Good.
Okay. Hi, everybody. This is our first formal lab of this semester. And for this lab, we focus on charges using balloons. I'm Katie.
I'm Evan.
I'm Scarlett.
So for the motivation and background regarding this formal lab, the task was to create an experiment to measure the charge on a pair of balloons. So we used two. And some background information that's required to understand this experiment and the trials that we ran is Coulomb's law, which basically explains that the two forces of attraction or repulsion within two charged systems is directly proportional to the product of their charges and inversely proportional to the square of the distance between them. And then this is also basic background information. Like charges attract each other, opposite charges repel. And then in this image here below, we have Coulomb's equation that's representing Coulomb's law. So we have Fe as the Coulomb force, Ke as the Coulomb constant, which will always be 8.987 or 8.99 times 10 to the 9th. And then for Q1 and Q2, those are both the charges or the sign magnitudes of the charges. And we have R as the distance between the charges and R, so the distance is squared in this equation. So for our project outline and setup, basically we had two medium-sized balloons. The mass of those were 3.60 grams each, so they were both the same mass. We had a string which was 76 centimeters in length. Half length would be 38 centimeters. For our first trial, we rubbed each of the balloons on the material cotton. For the second trial, we rubbed both of the balloons on the material denim. We also used a yardstick, a camera to film, tracker to input the data.
All right, so these are our models for our system. And so here's our system schema representing all the balloons. And so our things that we're focusing on are the balloons together with the string. And then our free body force diagrams, we're looking at each of the balloons. They are repelling each other since they are like charged. And then they're also experiencing force of tension from the string. And then here are our energy bar charts. They show initial, middle, and final. So the initial is when the balloons are closer together and basically touching. So there's going to be more kinetic energy. And then as they're moving away, they're gaining more potential energy. And at their furthest point, they have mostly potential energy. And so here's our trial number 1 tracker data. This is where we rub the balloons together on cotton. And so how I calculated this is I found the angle using the protractor on tracker between the balloons at the furthest point. And then I tracked each of the balloons up until they reached the furthest point of distance. And then here are the graphs for the position graphs for them. Mass A is the red balloon, which is the top right, and mass B is the blue balloon. And then the time at which they're furthest apart is 49.5 seconds. So that's the point where which we calculated the angle between the two balloons.
Here are the calculations for trial 1. As you see, we set the force tension equal to the force electric. And using that, we can find the charge of Q. And since we are assuming both the charges are equal, we just put that as Q squared.
So here's our tracker data for trial number 2. Again, mass A is the red balloon, mass B is the blue balloon. The angle for these is 28.5, and then the furthest point, the time that they are furthest apart is at 22 seconds. So that's when we measured the angle and the distance. And then here are the graphs measuring the x component of the position with the time at 22 seconds.
And then for our second trial calculations, we use the exact same data, but just different information to calculate it. So the limitation in air sources, some problems we were running into while conducting our experiment was getting a good enough charge for the balloons to be repellent. A lot of the times, the balloons were attractive to other things such as our clothing or the wall. Also, we know the HVAC system might have played an effect with the forces between the balloons, and it was hard to track the balloons on a single part when setting them up. That led to them spinning a lot, and then that led to some tracking error. We ran out of time to get another trial data as we tried many different objects and ways to chart the balloons, but they were attracted to each other rather than repellent. The conclusion results, we found that the charge of the balloons was 1.85 times 10 to the negative 7th and 5.57 times 10 to the negative 7th. Since the balloons should be similar charge with the same sign, since they were repelling. This is interesting because sometimes when we ran this experiment, they repelled and sometimes they were attractive, even when rubbing the balloons the same way. This is important so we can get a better understanding of charges act as a field, and we get a better understanding of electric fields. And that is our presentation. Thank you.